So our learning target from yesterday was I can describe and compare data sets. We were really just working on the describing. We learned some measures of center, which were mean and median. We learned some measures of spread, which were range and interquartile range. And we can use those to describe data sets. Today, we're actually going to learn one more measure of spread. And then we can use this measure of spread to help us describe data. So just like the range and interquartile range, another measure of spread is called standard deviation. Okay? The definition for standard deviation is that it represents the average of the distances between data values and the mean. It represents the average of the distances between data values and the mean. It tells us how far apart all the numbers are. It tells us how far they are spread out. That's why it's a measure of spread. So once we know the mean, we can kind of figure out, okay, how close are the other data values? We're going to find the distances between our data and the mean. We have done something really similar to this before. Actually, once we get into the lesson, you're going to feel like some of this is really familiar. If you remember back, trying to connect this lesson to something we've done in the past, we did a lesson about linear regression and exponential regression. In those lessons, we used GeoGebra to find the line of best fit for our data. Remember that that line of best fit, it kind of represents the average or the mean of all that data. Then what we figured out was, okay, if this is the line of best fit and it kind of represents the average of the data, how far apart are the actual data points and that line? Are they really close to the line or not so much? If they were pretty close, we felt like it was a good line of best fit. If they were not very close, we felt like it was not a great line of best fit. Today we're going to talk about standard deviation, which is really, really similar, okay? The distances between data values and the mean. If we want to figure out how far is the data from the mean, what do you think we probably have to calculate first? The mean, right? So let me give you some data. Let's pretend that it's finally April. It's coming up close enough, right? And we're going to record the temperatures for the first 5 days. The first 5 days of April, it is 77, 86 degrees, 84, 93, and 90. Clearly, we have moved away from Wisconsin, right? 93 degrees in April. So let's pretend those are the first 5 temperatures of April. If we want to figure out the standard deviation of this data so that we can use it to describe the data, the first thing we're going to have to calculate is the mean. So let's grab our calculators and find the mean. Remember to do the mean, we add the values of data together, and then we divide by how many there are. We're talking about 5 days. Okay. So we add those together, divide them by 5. Our mean comes out to be 86. Okay. Now, what we're trying to find is the average of the distances between our data, these 5 pieces, and this mean. So we're going to create a table. Make sure you have enough room to do this. The first thing that we need in our table is our data value. That would be our X, our input. Then we're going to find the deviation from the mean. So how far away from the mean is that number? Then we're actually going to do something to that distance. Do you guys remember back to the linear regression, exponential regression? When we figured out how far, really think about this with me, how far the point was from the line, some were above the line of best fit and some were below, right? So that means some were positives and some were negatives. But we didn't really care whether they were above or below. We just wanted to know how far. So what did we do to the numbers to eliminate the positives and negatives of them because we didn't care about that? We squared them. Yep. So that's what we're going to do here today. We're going to do the squared deviation. Because we don't care whether the temperature is above the mean or below the mean, positive or negative. We just want to know how far, the distance. So if we square them, it gets rid of all the positives and negatives. So that's our table. Okay. So our data values, we had 5 of them, 77, 86, 84, 93, and 90. And then the deviation from the mean. How far is 77 from 86? That's subtraction, right? 77 minus 86 is negative 9. Okay? And then we don't care if it was above or below. So instead of the negative 9, we're going to actually take that value and square it. We're going to get 81. So now that we've filled in the data, we have to talk about what do these standard deviation numbers tell me? Okay, great. The square of the distance that this number is from the mean is 81. So what? Right? Well, we actually want to know the average of that number, right? We want to know, like, on average, how far away are they? So what we're actually going to do is take these and we'll find the mean of them. So we're going to do 81 plus 0 plus 4 plus 49 plus 16. And then still divide it by 5 of them. Okay. And that'll give us the mean of the squared deviations. If I remember correctly, that comes out to be 30, right? But we still have the same question. So what? What does 30 tell us? 30 tells us that the mean distance of the squares from the mean is 30. We don't really care how far away the squares are though, right? We only did the squared because we wanted to get rid of the positives and the negatives because we didn't care whether they were above or below. But we don't want to know how far the squares are. We want to know how far away are the actual numbers on average. So if we squared our deviations to get this, how would we get back to our actual deviations? You do the square root because that's the inverse. So if we do the square root of 30, and we can round it because it's irrational, we can just make it 5.5. 5.5 is the standard deviation. So if the 5.5 is the standard deviation, here's what that tells me. It tells me that on average, the data points are about 5.5 away from the mean. Okay? On average, my 5 data points, my 5 original temperatures, are about 5.5 away from the mean. Okay? Now, here's the deal. That tells me that they're pretty closely grouped because that number is pretty small. If you look at these, are they pretty closely grouped? Yeah, really, 77 to 93. What if we threw in a random number that was way out of this area, like 34? Thunderstorm rolled in, got really cold and windy, and the 6th day was 34 degrees. Don't you think this would be considered an outlier? Like later in the module, we're going to learn how to actually calculate if it's an outlier or not, like to prove it. But if I had to guess, I'd say that's an outlier. What is this outlier going to do to our standard deviation? This is telling me that they're pretty closely grouped. Because on average, the numbers are only about 5.5 away from the mean. Okay? The mean is definitely going to change, right? The mean is not going to be 86 degrees anymore. But the standard deviation is going to change a lot too. Because they're way more spread out now because of this outlier. This number will be much bigger. And what it would tell me then is it would tell me that the numbers are not quite as closely grouped as they were before because this one is so far out. Okay? What I want you guys to do is figure out what the standard deviation number would be if we had that 6th value in there. Here's our conclusion. It's approximately 20. We did some rounding. But it went from about 5.5 to about 20 because of one number. So what this tells me is that they are a lot more spread out now. And of course they are because of that 34, because of that outlier. The standard deviation was affected a lot by that one outlier, wasn't it? Do you think that this is a really good representation of the data? Like if I told you that on average, numbers were 20 away from the mean. Is that really accurate? Not really. They're actually all really close to the mean except for that one. So here's what this is telling you. Yes, that is a statistic we can use to describe the data, but in this scenario, it's actually not a very good description. It doesn't really show us what the data is like. Now, for the other set that did not have the 34 degrees in it, the standard deviation was a really good description. It told us that they were all packed pretty closely together, which was actually true. So here's what you're supposed to take away from this problem. Here's the main idea. We now know how to find the mean, median, range, interquartile range, and standard deviation. Those are all statistics we can use to describe data. But some of them are better descriptions than others, depending on what data we're working with. So sometimes one is better to use than another, but it all depends on what your data set looks like. Okay? For the first data set that did not have the 34 in it, I think the standard deviation is a good number to describe it. For this set with the 34 in it, I don't think this is a good descriptor at all. What would be a better descriptor for the data set that has 34 in it? What is one of the other ones that we learned that maybe wouldn't change all that much with this outlier in there? The median. The median actually wouldn't change much. Think about it. We're just adding one number. Let's see if we can figure the median out. They're not in order, but we can be, here's the low, here's the high. Then the next high and the next low, and then these two are in the middle. So the median is 85 degrees. Do you think that that would be better to talk to somebody about? Like, hey, the median's 85 degrees, as opposed to telling them the standard deviation is 20, meaning they're way spread out, which they really aren't. It's just the one. So in this scenario, it'd probably be better to talk about the median than to talk about the standard deviation. What about the mean? Would the mean change a lot here? We know that it kind of did, right? It went from 86 to 77. But even that's a better descriptor than the standard deviation, don't you think? It did go down quite a bit, but not as much. So once again, here's your main point again. Your main point is all these statistics can be used to describe data, but sometimes one's better than another, depending on what your data looks like. Okay? The tables list the average ages of players on 15 teams randomly selected from the 2010 teams in the National Football League and the Major League Baseball. Calculate the mean, median, interquartile range, and standard deviation of each set. And describe how the average ages of NFL players compare to those of Major League Baseball players. Compare. That was the second part of our learning target, right? To learn how to do the statistics, but then how to use it to compare data. So, if we entered all this information and all the Major League Baseball information, here's the statistics that we would get. Okay? So, for football, the mean age is 25.98. For baseball, it's 28.62. So the mean age for baseball players is higher than football players. Does that sound right to you? It does for me, because I know that baseball players tend to have longer careers. They play till they're older because I think it's less abusive on your body. So it does make sense to me that the mean age is a little bit higher. Okay? The median age for baseball is also a little higher, which also makes sense to me that the middle age would be a little bit higher, knowing that baseball players tend to play until they're older. Okay. Now, the interquartile range, this is where it kind of gets interesting. Remember that the interquartile range is the range, but only of the middle people, the middle 50%. When you find the interquartile range, who gets excluded? The top 25%, which are the old guys, and the bottom 25%, which are the really young guys. All the outliers too, right? Like the one weird kicker who's 42 years old and still in the NFL, or the one pitcher that lasts till he's 40. Those guys would not be considered in this interquartile range, because the interquartile range is the range of just the middle. So Major League Baseball is larger. That means the spread of the people in the middle is bigger. And then our standard deviation number. The standard deviation, so the standard deviation number is higher. And what that means is that all of the data values are spread farther away from the mean than they are for football. And that does make sense to me, because like I said, I know that there are some baseball players that are much older than NFL players. And the other thing is, I think baseball players get into the major leagues younger. So that's a difference too, because for football, they pretty much wait till their junior or senior year of college, whereas baseball, sometimes they're coming right out of high school or a year out of high school. So it makes sense to me that they are more spread apart from the mean. Okay? And if you look at the book's conclusions, they say exactly that. They say the interquartile range and the standard deviation are smaller for the NFL. So we know that the ages of the NFL players are closer together than those of the Major League Baseball players. Okay.